Let's consider the following statements to check if each of them is true or false. The first statement is, for any set A is a subset of itself. Is this claim true or is it false? If we go back to the definition of the subset relationship, A is a subset of B if every element of A is also an element of B. So what if we replace B by A over here? Is every element of A also an element of A? Well, yes, that's trivially true. So we can say that A is a subset of itself, regardless of what the set A is. So this statement is true. Let's come to the second statement. Is the empty set a subset of any other set S? If you go back to this diagram where we showed the subset relationship by representing A and B as circles, you can think of the empty set as a set that has no dots inside it because it has no members in it. Now such a circle can be put anywhere. It could be put here, it could be put here, it could be put inside any set, and it would make absolutely no difference because after all its contents are blank. So you can take any blank region and put the empty set there, and we can make this circle as small as we wish so that it fits inside any set. So it would make sense for us to claim that the empty set is a subset of every other set. The third claim is that Q, the set of rational numbers, is a subset of R, the set of real numbers. Is this claim true or false? Well, this claim is true because every rational number is also a real number. And of course the set of real numbers has other numbers which are not rational. Irrational numbers are also real numbers. So the set R has all the elements of the set Q, and it has more elements. It has irrational numbers as well. So Q is really a subset of R. The fourth claim is that A is a subset of B where A and B are defined in the following way. A is a set of objects X such that X divides 56. So A is basically the set of all factors of 56. B is the set of all the prime factors of 56. Is A a subset of B? Well, anything that's a prime factor of 56 must be a factor of 56 as well. But it's not necessary that a factor of 56 must necessarily be a prime factor of 56. For example, if we take the number 28, 28 is a factor of 56. But 28 is not a prime number. So it's not a prime factor of 56. But if we take a prime factor of 56, say the number 2, 2 is clearly a factor of 56 as well. So anything that's an element of set B must be an element of set A as well. But the converse is not true. So it's actually B that is a subset of A over here. So the claim that A is a subset of B is false. Let's now come to the fifth statement. The claim is that A is equal to B, where A is defined to be the set 1, 3, 5, and B is defined to be the set of all objects X such that X is a natural number and X is odd. So B is really the set of all odd natural numbers. So clearly the sets A and B are not equal because A has just 3 elements whereas B has an infinite number of elements. So this is false. But what if we were to add the condition that X belongs to N and X is odd and X is less than 6? With this added condition that X is less than 6, the set B is now constrained to have what elements? Well, to be a natural number less than 6, the only options are 1, 2, 3, 4 and 5. And if you look at the added constraint that X must be odd, 2 and 4 get eliminated. So now we are left with only 3 possible members of the set B, which are 1, 3 and 5. So if we define B in this way, then B would be 1, 3, 5 in roster form, and clearly A and B would then be the same. The last claim is that B is a subset of A, where A is the set of all vowels in the English alphabet, whereas B is the four element set A, B, C, D. Is every element of B also an element of A? Well, clearly not. If you look at B, C, or D, none of these three elements is present in the set A. So B cannot be a subset of A.